Welcome to our deep dive into electromagnetic waves. In this chapter, we'll explore the fascinating world of M waves, starting from the fundamental Maxwell's equations to their wide-ranging applications in daily life and technology. Electromagnetic waves are all around us, from the light we see to the radio signals we use for communication. Understanding how these waves work not only helps us appreciate the science behind modern technology, but also gives us insight into the natural world. Let's begin our journey by looking at the foundational principles that govern electromagnetic waves. The heart of electromagnetic theory are Maxwell's equations. These four equations elegantly summarize the behavior of electric and magnetic fields and how they interact. They are Gauss's law for electricity, Gauss's law for magnetism, Faraday's law of induction, and Ampere's law with Maxwell's addition. Together, these equations show that changing electric fields produce magnetic fields and vice versa, leading to the propagation of electromagnetic waves. Maxwell's equations are considered one of the greatest achievements in physics, unifying electricity, magnetism, and optics into a single framework. Let's derive the wave equation for electromagnetic waves. By combining Maxwell's equations, we find that both electric and magnetic fields satisfy a wave equation. This equation describes how these fields propagate through space at a constant speed. The derivation involves taking the curl of Faraday's and Ampere's laws and applying vector calculus identities. The result is a second-order differential equation, which has solutions representing waves traveling at the speed of light. This mathematical foundation is crucial for understanding how M waves move and interact with their environment. Displacement current is a key concept introduced by Maxwell to address a gap in Ampere's law. It refers to the changing electric field in a region which acts like a current and produces a magnetic field, even in the absence of actual charge flow. This idea was essential for the consistency of Maxwell's equations and for predicting the existence of electromagnetic waves. Displacement current bridges the gap between static and dynamic fields, allowing for the seamless propagation of M waves through both conductors and insulators. Electromagnetic waves are generated whenever electric charges accelerate. For example, when an antenna oscillates electrons back and forth, it creates changing electric and magnetic fields that radiate away as M waves. This process is fundamental to how radio, television, and many wireless technologies work. The generation of M waves is not limited to artificial sources. Natural phenomena like lightning also produce them. Understanding this process helps explain the origin of the vast spectrum of electromagnetic radiation we observe. What exactly are electromagnetic waves? They are transverse waves consisting of oscillating electric and magnetic fields which are perpendicular to each other and to the direction of propagation. Unlike sound waves, M waves do not require a medium and can travel through a vacuum. This unique nature allows them to move freely through space, carrying energy and information across vast distances. The dual electric and magnetic components make M waves incredibly versatile and essential in both nature and technology. One of the most remarkable properties of electromagnetic waves is their speed. In a vacuum, all M waves travel at the speed of light, approximately 3 times 10^8 meters per second. This speed is determined by the electric permittivity and magnetic permeability of free space. In other media such as glass or water, M waves slow down due to interactions with the material. The constancy of the speed of light in a vacuum is a cornerstone of modern physics and underpins many scientific theories. Electromagnetic spectrum encompasses all types of M waves, arranged by frequency or wavelength. It ranges from long-wavelength radio waves to short-wavelength gamma rays. Each region of the spectrum has unique properties and uses, from communication to medical imaging. Understanding the spectrum helps us harness different types of M waves for specific applications, making it a vital concept in science and technology. Radio waves are the longest wavelength M waves, used extensively in communication systems. They are generated by oscillating electric currents in antennas and can travel long distances, making them ideal for radio, television, and mobile communication. Radio waves can penetrate through buildings and the atmosphere, allowing for reliable transmission of information. Their low energy makes them safe for everyday use. Radio waves have a wide range of applications beyond broadcasting. They are used in navigation systems like GPS, remote controls, and wireless networking. In medicine, radio waves are used in MRI scans to create detailed images of the body. Their ability to travel long distances and penetrate obstacles makes them indispensable in modern technology and daily life. Microwaves have shorter wavelengths than radio waves and are widely used in communication and cooking. In telecommunications, microwaves transmit data over long distances, especially in satellite and cellular networks. In the kitchen, microwave ovens use these waves to heat food quickly by causing water molecules to vibrate. Microwaves are also used in radar systems for weather forecasting and air traffic control. Infrared waves fall between microwaves and visible light in the M spectrum. They are primarily associated with heat, as all warm objects emit infrared radiation. Infrared technology is used in remote controls, thermal imaging cameras, and night vision devices. In medicine, infrared waves help in physical therapy and diagnostics. Their ability to detect heat makes them valuable in a variety of fields. Infrared waves are used in many practical applications. In addition to remote controls and thermal cameras, they are used in fiber optic communication, where infrared light transmits data through glass fibers. Infrared sensors are also used in security systems and automatic lighting. Their ability to sense heat and transmit information makes them crucial in both consumer electronics and industrial processes. Visible light spectrum is the portion of the M spectrum that can be detected by the human eye. It ranges from violet to red, with each color corresponding to a specific wavelength. Visible light is essential for vision, photosynthesis in plants, and countless technological applications like photography and displays. The study of visible light has led to the development of optics and has greatly advanced our understanding of the natural world. Ultraviolet UV rays have shorter wavelengths than visible light and are invisible to the naked eye. UV rays are responsible for causing sunburns and are used in sterilization and disinfection processes. They are also important in the production of vitamin D in the skin. However, excessive exposure to UV rays can be harmful, so proper protection is necessary when dealing with strong UV sources. Ultraviolet rays are widely used in various industries. In healthcare, UV lamps sterilize medical equipment and purify water. In forensic science, UV light reveals hidden substances and fingerprints. UV rays are also used in curing inks and resins in manufacturing. Their ability to kill bacteria and viruses makes them invaluable in maintaining hygiene and safety. X-rays have even shorter wavelengths and higher energy than UV rays. They are best known for their use in medical imaging, allowing doctors to see inside the body without surgery. X-rays are also used in security scanners at airports and for inspecting materials in industry. While X-rays are extremely useful, exposure must be controlled to avoid health risks. Gamma rays are the highest energy M waves produced by radioactive decay and certain cosmic events. They are used in cancer treatment to destroy malignant cells and in sterilizing medical equipment. Gamma rays can penetrate most materials, making them useful for imaging and industrial inspection. Due to their high energy, gamma rays are hazardous and require careful handling. Polarization refers to the orientation of the electric field in an electromagnetic wave. In unpolarized light, the electric field vibrates in all directions perpendicular to the direction of travel. Polarized light, on the other hand, has its electric field oscillating in a single direction. Polarization is used in sunglasses to reduce glare in photography and in various scientific instruments. It's a key property that helps us control and utilize M waves more effectively. Reflection occurs when electromagnetic waves encounter a surface and bounce back. This phenomenon is responsible for the images we see in mirrors and the functioning of radar systems. Reflection is governed by the law of reflection, which states that the angle of incidence equals the angle of reflection. Understanding reflection is essential for designing optical devices and communication systems. Refraction is the bending of electromagnetic waves as they pass from one medium to another with a different density. This effect is why a straw appears bent in a glass of water. Refraction is crucial in the design of lenses, glasses, and optical fibers. It enables us to focus light and transmit information efficiently over long distances. Refraction occurs when electromagnetic waves encounter an obstacle or opening and spread out as a result. This property allows waves to bend around corners and is responsible for phenomena like the spreading of light through a narrow slit. Diffraction is important in understanding the behavior of waves in various environments and is used in technologies like diffraction gratings and spectroscopy. Interference is the phenomenon where two or more electromagnetic waves overlap and combine to form a new wave pattern. This can result in constructive interference, where waves add up, or destructive interference, where they cancel each other out. Interference is observed in patterns like those seen in soap bubbles or thin films and is fundamental to technologies like noise-canceling headphones and holography. Electromagnetic waves are the backbone of modern communication systems. They carry information over vast distances, enabling radio, television, mobile phones, and the internet. By modulating the properties of M waves, we can encode and transmit data efficiently. The versatility and speed of M waves make them indispensable in connecting people and devices worldwide. Summarize, electromagnetic waves are a fundamental aspect of physics, with applications ranging from communication to medicine. Maxwell's equations provide the theoretical foundation, while the M spectrum offers a wide variety of wave types, each with unique properties and uses. Understanding M waves allows us to harness their power for countless technological advancements. Gauss's law for electricity states that the electric flux through a closed surface is proportional to the charge enclosed. This law helps us understand how electric fields originate from charges and how they distribute in space. It's a cornerstone for analyzing electric fields in various configurations, from simple point charges to complex systems. Gauss's law for magnetism states that the net magnetic flux through any closed surface is zero. This means magnetic monopoles do not exist, magnetic field lines always form closed loops. This law is essential for understanding the behavior of magnetic fields and is one of the four Maxwell's equations. Faraday's law states that a changing magnetic field induces an electric field. This principle is the basis for electric generators and transformers. Faraday's discovery revolutionized technology, enabling the generation and distribution of electricity on a large scale. It's a key concept in both physics and engineering. Ampere's law relates magnetic fields to electric currents. Maxwell's addition, the displacement current, extends this law to include changing electric fields. This correction was crucial for predicting electromagnetic waves and unifying the laws of electricity and magnetism. Ampere's law with Maxwell's addition is fundamental to understanding how M waves are generated and propagate. Wave equation for electromagnetic waves is a second-order partial differential equation. It shows that both electric and magnetic fields propagate as waves at the speed of light. The mathematical form of the wave equation allows us to predict how M waves behave in different environments, from free space to complex materials. Electromagnetic waves share several key properties. They are transverse, can travel through a vacuum and carry energy and momentum. Their speed depends on the medium, and they can be reflected, refracted, diffracted, and polarized. These properties make M waves incredibly useful in a wide range of scientific and technological applications. Electromagnetic waves are an integral part of our daily lives. From the sunlight that warms us to the Wi-Fi signals that connect our devices, M waves enable countless conveniences. Understanding their properties helps us use them safely and effectively, whether it's protecting ourselves from UV rays or optimizing our communication networks. Radio waves are the foundation of wireless communication. They are used in broadcasting, mobile phones, and satellite links. By modulating the amplitude or frequency of radio waves, we can encode information and transmit it over long distances. This technology has revolutionized how we share information and stay connected. Microwaves are used in point-to-point communication links, satellite transmissions, and radar. Their shorter wavelength allows for higher data rates and more focused beams. Microwave communication is essential for modern telecommunications infrastructure, enabling fast and reliable data transfer. Infrared waves are widely used in technology, from remote controls to thermal imaging. They allow us to detect heat, transmit data through optical fibers, and see in the dark with night vision devices. Infrared technology continues to evolve, finding new applications in security, healthcare, and entertainment. Visible light is crucial for science and technology. It enables us to see, study the universe with telescopes, and develop advanced imaging techniques. The manipulation of visible light has led to innovations in photography, microscopy, and display technologies, enhancing our ability to observe and interact with the world. Ultraviolet rays play a significant role in scientific research. They are used to study chemical reactions, detect biological materials, and sterilize equipment. UV spectroscopy is a powerful tool in chemistry and biology, allowing scientists to analyze substances at the molecular level. X-rays have revolutionized medicine by providing a non-invasive way to look inside the body. They are used to diagnose fractures, infections, and tumors. Advances in X-ray technology have improved image quality and reduced exposure, making medical imaging safer and more effective. Gamma rays are used in industry for inspecting materials, detecting structural flaws, and sterilizing products. Their high energy allows them to penetrate thick materials, making them ideal for quality control and safety inspections. Gamma rays are also used in scientific research to study atomic and nuclear processes. Modulation is the process of varying a property of an electromagnetic wave to encode information. Common types include amplitude modulation (AM) and frequency modulation (FM). Modulation allows us to transmit audio, video, and data over M waves, forming the basis of all wireless communication systems. While electromagnetic waves are essential to modern life, safety is important. Some M waves, like X-rays and gamma rays, can be harmful in high doses. Proper shielding and exposure limits are necessary to protect health. Understanding the risks and benefits of M waves ensures their safe and effective use. Electromagnetic waves are not just man-made, they occur naturally as well. Sunlight, lightning, and cosmic radiation are all examples of natural M waves. These waves play a vital role in ecosystems, weather patterns, and the overall functioning of our planet. Studying natural M waves helps us understand the universe and our place within it. Future of electromagnetic wave technology is bright. Advances in wireless communication, medical imaging, and energy transmission continue to push the boundaries of what's possible. Emerging fields like quantum communication and terahertz imaging promise even greater innovations. Staying informed about M-wave technology is key to understanding and shaping the future. Let's review what we've learned about electromagnetic waves. We covered Maxwell's equations, the wave equation, and the entire M spectrum. We explored the properties, applications, and safety considerations of M waves. This knowledge forms the foundation for understanding modern science and technology, empowering us to make informed decisions and innovations. Conclusion: electromagnetic waves are fundamental to both the natural world and human society. From enabling communication and medical advances to shaping our understanding of the universe, M waves are truly remarkable. By mastering the concepts in this chapter, you gain a deeper appreciation for the science that powers our modern world and the endless possibilities that lie ahead.